Hello, everybody. If you thought things were getting weird when we started to talk about black holes and possibly breaking physics, well, things are about to get really strange, mind-bogglingly strange. And this is with physics we know. We are about to start our discussion on relativity. And we will start our discussion with special relativity. And the way that we'll generally go through this is we'll take a look at what Einstein's special and general relativity, what relativity is, and then we're going to look at some of the interesting consequences of relativity. All right, so now that I have the right slides up, let's go ahead and get started. And since we're going to be talking about Einsteinian relativity, I have to start with a picture of Einstein actually working on the board. And the equations that you see on the board are special relativity equations. We're not going to be doing that, so don't worry. We're going to talk about the concepts of special relativity. Why are we doing this? Well, in those extreme regions, like right outside the event horizon of a black hole, near the surface of a neutron star, in any area where there's an intense amount of gravity, we're going to have to deal with relativity. That's when relativity becomes important and we can no longer rely on Newton's laws of motions. We also have to consider relativity whenever things are moving at extremely high velocities. So, in both of these scenarios, which are quite common throughout the universe, but very rare for here on Earth, hence us never really dealing with them, and these being some of the biggest modern breakthroughs of physics, because we don't observe them here on Earth. But out there in outer space, these conditions are pretty common, pretty normal. And we can't use Newton and Newton's laws of motion and Newtonian gravity any longer. We have to go to something that deals with these scenarios. We have to move to Einstein's theory of relativity. Now, I want to be clear that when we're talking about moving at extremely high velocities, what this means is typically if you're moving at about 10% the speed of light, zero point 0.1 times the speed of light, or larger, then you really have to start accounting for special relativity corrections. So you have to do your relativistic corrections once you start moving at about 10% the speed of light or faster. We call such fast speeds relativistic speeds. And now, whenever you watch all the television shows and the movies where people are going, they're moving at relativistic velocities and things like that, you know what they're trying to reference to, but they're usually doing a pretty bad job. And they're referencing, you are now getting to the point where you're moving past the bad science that most movies have. Okay, so if we're going to look at Einstein's theories of relativity, let's take a look at just in general what he was up to. Because these ideas didn't just spark and they weren't done all at once. He built this idea over time. So he has two theories. And whenever we talk about the theory of relativity, we're talking about these two theories combined into a larger theory. So we have special relativity, which was how he pretty much started this issue. And he published this work in 1905. And then he worked towards a greater publication about general relativity, which sort of encompassed the results of special relativity and made them generally applicable to the entire universe. So in 1915, he released general relativity. And then if we take all of the lessons learned from all of that, we just call that Einstein's theory of relativity. And amazingly, these were mostly developed. I mean, there was a lot of mathematical work that was done, but the inspiration for these were mostly done with thought experiments. Einstein is relatively famous for one of his early teenage thoughts is he sat around and instead of thoughts that you might expect teenagers to have, he was imagining what the universe would look like if he was riding on a beam of light. So he was imagining what the universe would be like in all of these interesting scenarios. Whenever you actually put some physics behind that and you think about a scenario and then how the physics would play out in that, you're conducting what we call a thought experiment. And that's how Einstein developed most of relativity, is through thought experiments. For us to understand special and general relativity, and this video will focus on special relativity, we first have to understand what is encompassed in the term frame of reference or reference frames, because this is absolutely important. It is a foundation cornerstone to understanding relativity, to understand what reference frames are. And it's a pretty fancy sounding term, and it's really easy to overthink this one. So I'll make this plain and simple. A frame of reference, or simply what we call a reference frame, is just a place where an observer is making observations. So it's a spot to make observations from. It is a place to conduct an experiment, which that doesn't sound that bad. So let's go ahead and take some looks at frames of reference. So a reference frame would be me. I'm in my apartment. I could look out the window and I could observe the cars on the highway. I could watch people walking down the sidewalk. I can observe the outside world from my reference frame of here in my apartment. Maybe your reference frame is from the inside of a train, and you're looking at the world as your train goes by, and you see all the people at the train stop, or you see the trees in the background moving, things like that. At that point, you on the train, that's your reference frame where you're making observations. Somebody that's maybe sitting on the train platform would be making observations from the platform and be watching the train go by. They would be in a different reference frame. Play the same game if you wanted to do that with an airplane. Somebody looking out of the window of an airplane, the on the airplane is a reference frame, and then you on the ground watching the airplane fly by, you're in a different reference frame watching the airplane fly by. An astronaut on the International Space Station looking down at the Earth. And now, I guess just to really hammer this point in, let's go back to the train and let's consider what things look like from the perspective of me. Let's imagine that I'm not in a room, I'm in a train car, and let's say the train is moving down the tracks at 100 miles per hour. I'm in a nice train car, so in my reference frame, if I have a ball, I can just toss it, I can just toss it up and down. It looks like it's going straight up and straight down. Now imagine you're standing in a different reference frame, you're at the train station, and you watch me on my train go by. I'm just sitting here tossing a ball straight up and straight down. But for you, it would look like the ball is getting tossed up. And then as the train moves, you see the ball moving with the train. So it carves an arc through the sky. So clearly what you're observing depends on what reference frame you're observing from. If you're observing from one reference frame and looking at something else, you might observe something different. And this is going to be key to understanding how relativity works. And then whenever things really start getting weird is consider a reference frame of a spaceship that's moving at relativistic speeds. What kind of things are they going to observe if they're looking at the window? If you have two spaceships moving at relativistic speeds and they fly past each other, what do they observe about each other? All right, so now let's start diving into the weird and start with special relativity. And the way I'll do this is we'll go through some of the thought experiments that that Einstein went through, and then we're going to look at some of the consequences that come out of these pretty simple to understand, but mind-boggling the second you really start to digest and churn through the consequences of what these theories are telling us. So we're going to start with special relativity, which was published in 1905. The formal name is the Special Theory of Relativity. We usually just say special relativity. And the theory of special relativity rests on two postulates. So just generalized principles, that's what I mean whenever I say postulates. The first one is what we call the principle of relativity. Pretty aptly named, right? So the principle of relativity states that all motion is relative. Okay, yeah, that sounds like a principle of relativity. All motion is relative. What does that mean? That means that there is no special reference frame. There's no single observational frame from which you can be in that reference frame and use that as your absolute standard of motion for the rest of the universe. There is no set absolute reference frame on which you can judge all other motion in the universe. All reference frames have to be considered relative to the other reference frames, and none of those reference frames are special. So there is no absolute reference frame on which we can set a universal standard by. So really we're saying that yes, everything is relative to how other things are moving around. And this is the principle of relativity. All motion is relative. The second postulate, the invariance of the speed of light. And I've alluded to this several times throughout the semester. That the speed of light is constant. We know that nothing can go faster than it. So the speed of light is constant and it is the fastest that something can move. But the invariance of the speed of light Means that it doesn't matter what reference frame you're in and what reference frame you're observing, you always, always, always measure the speed of light to be the same. It doesn't ever vary. When you measure the speed of light, you always get the same answer. You always get the same number. And the number is here on the screen. It's about 3 times 10 to the 8th meters per second, 300,000 kilometers per second. Ridiculously fast. It doesn't matter what reference frame you're in. It doesn't matter what reference frame you're observing from your reference frame. You always measure the speed of light the same in every experiment across all reference frames. It never varies. It's always the same. The speed of light is the speed of light is the speed of light. Now, that is where we're going to see some pretty drastic consequences. And let's start pretty light. Let's start with a non-relativistic scenario. And I know this image is pretty dated, but I just love it so much because it is so ridiculous. Because this is a scenario I can never imagine. But sure, let's just roll with it. Let's lean into it. So let's consider the following scenario. Here we have a person in a car, and for some reason, this guy with a clipboard is like, yes, this looks like something I would like to calmly observe. So this person in the car is driving down the road at 100 kilometers per hour. He also has a gun, because why not? And with the gun, he fires it out the window, bang, 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 bang. And the bullets, so the kind of gun he has, fires bullets at 1,000 kilometers per hour. Okay, so for the reference frame of the person in the car, the bullets look like they're speeding away from him at 1,000 kilometers per hour. What does the observer in the reference frame of standing calmly and watching some guy go down the road firing a gun out, bang, 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 bang? What does that person observe? Well, they see the person in the car with the gun that's moving 100 kilometers per hour, and then they fire a bullet. The gun fires that bullet at 1,000 kilometers per hour. So if this person were to measure the speed of the bullet, and this is not really a big surprise to you, they would measure the speed of the bullet to be the speed of the car, 100 kilometers per hour, plus the speed of the bullet, 1,000 kilometers per hour. The bullet would be traveling at 1,100 kilometers per hour. This becomes pretty intuitive if you think about, okay, here I am on a train and I have a medicine ball. Let's take a scenario where I just boarded the train and I'm not moving compared to you. We're in the same reference frame, and I toss you the medicine ball. You'd probably go, oof, but you'd catch it. Now let's imagine now, so maybe I toss the medicine ball like 5 miles per hour and you caught it. Now let's imagine I'm on a train that's speeding towards you, and I lean out of the train and say I'm going 50 miles per hour on the train. And I take that medicine ball and I toss it to you, giving it an additional velocity of 5 miles per hour. Do you want to catch that medicine ball? No. Nobody wants to get hit with a medicine ball that's going 55 miles per hour. That would floor you and very likely kill you. So that's how we normally interact with the world. This makes sense to us. You add these speeds together. If the person were to fire the gun backwards, this person would observe the bullet moving at 900 kilometers per hour. If the car were moving 1,000 kilometers per hour this way, and they were to fire the gun backwards at 1,000 kilometers per hour, to this person, it would look like the bullet would just fall straight down. All right, now let's go weird and deal with the invariance of the speed of light. So here's a equally ridiculous scenario. And I don't know what's going on with this one either, but here we have this cool looking spaceship. Okay, cool might be relative here. And it's got a laser beam and it's gonna fire this laser beam. So instead of bang, 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 now we're pew, 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 pew. So, and for some reason, here's this guy on this space station, just like, cool, look at the spaceship go. And they're gonna do some observations. Same sort of scenario. Notice that this is 10% the speed of the bullet. So now let's make this spaceship is moving at 10% the speed of light. And it's going to fire its laser beams. Pew! And this laser beam will travel at the speed of light. It's firing light that moves at the speed of light. Now, intuitively, you want to think, okay, what does this observer see? Well, the spaceship's moving at 0.1 c and the light is fired at c. So it makes you want to think that this person would observe the speed of light to be 1.1 c, 10 times or 1.1 times faster than the speed of light. Except the invariance of the speed of light says, nope. What this what this person right here observes is they measured the speed of light in this scenario to be the speed of light. And it wouldn't matter if the spaceship is moving backwards, the other direction, at 10% the speed of light, or if it was moving in this direction at 99% the speed of light. If they fire their laser beams, and this person always measures the speed of that laser beam to be the speed of light. The speed of light is invariant, it's always the same. That seems weird and counterintuitive, but we can conduct experiment after experiment. This is fairly easy for us to confirm with modern technology, the invariance of the speed of light. This has some profound consequences. So let's dive in. And we're going to enter our first thought experiment, the consequence of the invariance of the speed of light. So now let's consider a person on a spaceship that has a laser beam, something that can fire a laser beam, and it has a mirror at the top. And then the laser beam can come back down and be detected. So this person on the spaceship is going to be moving very, very fast at 86% the speed of light. And they'll fire a laser beam, bounce it off this mirror, and it'll come back down. And what they're going to do is they're going to time how long it takes for the laser beam to go up, bounce off the ceiling, and come back down. They will be running that experiment while this observer, and I don't recommend just wearing jeans while you're standing outside of a spaceship in outer space with no helmet, probably gonna end up deads. But this person right here is watching the spaceship go by, and they're going to observe the laser beam as well. And they're going to time how long it takes the laser beam to go up, hit the mirror, and come back down and hit the floor at the detector. The key point is, remember that the speed of light is always going to be measured to be the same, and that there is no special reference frame. Okay, so now that we have this set up, over here in this box, what does the astronaut see? So what does this person see whenever they run the experiment? They watch this beam of light go up and come back down. So they see it go up, it bounces, and then it comes back down. It traveled, if the height from the floor to the ceiling here is h, it traveled h plus h to h. And I had some travel time, let's just call it travel time 0, t or t naught, some standard time. What does this person observe though? As the spaceship is zooming by them at 86% of the speed of light, they not only see the laser beam moving up and down, but also moving to the side. It is very similar to the idea of I'm on a train throwing a ball up and down, and you watch the train go by. It looks like the ball is carving an arc, except now we're playing that game with light, and the speed of light is constant. So this is what the person outside the spaceship sees. And I tried to make it so that beam is moving the same speed here as it is here. It's moving at the speed of light. Man, that's taking a long time to get all the way to the ceiling and back. Because from this person's perspective, the beam of light traveled not only this distance up, but to get there, it traveled this distance across. So the beam of light looks like it traveled this big long distance to bounce off the mirror, and then this big long distance to hit the detector here. So the travel distance is much larger than 2h, which means that the travel time is going to be much longer than what this person, this t naught, what the time that the person on the spaceship observed. That's weird. Same thing is happening. A beam of light is going up and going down, and here it goes this way and then back down this way. But the times are different. Why? Here, traveling at the speed of light, it traveled 2h very, very quickly. That time was not very long at all. Now, for this person observing, this person on the spaceship, They have to watch the beam of light travel still at the speed of light, but it travels a much larger distance, so it takes a longer amount of time. And that longer amount of time means that it looks like the astronaut who's measuring just the up down, it just makes it look like the astronaut's moving incredibly slowly. So if they were sneezing, the person on in the spaceship would just go, achoo. The person observing, they sneeze for the entire duration of the up down laser. The person observing from the outside would see, choo. Weird. And I worked out the math of it. For 86% in the speed of light, the sneeze would take twice as long for this person observing. It literally would look like the astronaut's moving really, really, really slowly if they both had clocks. When this person counts off a second, this person could count off a second. But if this person was timing how long it took it to go up and back down to complete the bouncing of the laser experiment, that'd be much longer, a much longer amount of time. The only way to resolve this is that the clocks are not running at the same speed. For this person, observing the person that's moving at a high speed, it looks like the person inside is moving incredibly slowly. Time is moving slower. We say that time has been dilated because this observer right here is seeing the same experiment. Laser goes up and back down. It takes a longer distance to get there, but light travels at a finite speed, so it takes it a longer amount of time to travel that longer distance, which means that it looks like time is going slower. And I know this sounds ridiculous, but it is confirmed by real experiments over and over and over and over and over again. Things that are moving faster have clocks that run slower. Time is relative. And brings us to some pretty profound consequences from special relativity itself. One is that the space that the spaceship was in, the fact that it was moving through space, changed how time was working, means that there's some intimate connection between time and space. They can't be considered as separate things. They have to be considered as one larger whole. And this is where Einstein came up with this idea of space-time, that space and time are somehow coupled together. And space and time cannot be considered independently. One depends on the other. They are components of a larger whole that we call space-time. So we live in at least 4 dimensions, 3 spatial dimensions and 1 time. Now, that doesn't mean that those dimensions are the same. I mean, space, you can move in different directions. You can move forward and backwards in space and in 3 different directions. Time, you can only move forward, and you can't change how fast, for your reference frame, time just always ticks at 1 second per second. It might not be the same if you're observing somebody else's reference frame, but it's always moving forward. So usually we say we don't live in a 4-dimensional universe. We live in a 3 plus 1 dimensional universe, 3 spatial dimensions plus 1 time dimension. Okay, consequence 1, space-time's a thing. Consequence 2, there is a thing called time dilation. So the time for an event to take place depends on what reference frame you're in and what reference frame you're observing. And if you're moving, or if you're observing a fast moving reference frame, so a person on a spaceship that's speeding by you about the speed of light, time appears to run slower. Even a person on a train that's going by you at 100 miles per hour, time is technically going slower for the people inside the train. Now, let's flip this. For the people inside the train, it looks like you're the one that's doing the moving, and they're sitting still. So they would say that your time is going slower. This is getting mind-boggling hard to deal with, but it comes down to a single point. For things moving faster than you, their clocks are literally running slower than your clocks. We can confirm this by flying airplanes around the Earth, putting atomic clocks on both. We can confirm this with GPS, which is moving around, it orbits the Earth once in 12 hours. We move around the Earth once in 24 hours. And we have to account, that means that their clocks are running slower. We have to correct for that because GPS does its positioning by basically doing timing experiments, measuring timing of pulses. So time is a critical factor. And if you don't account for the special relativistic corrections, GPS doesn't work. Something that we use every day depends on this being real. If you're ever curious about how to actually go through some of the calculations, you have to use what are called Lorentz transformations, which rely on this thing called the Lorentz factor. It's given by the Greek letter gamma, lowercase gamma, and it equals this, where v here is the velocity of the reference frame you're considering, so that spaceship moving past you at 86% of the speed of light, and c is just the speed of light. And then you can figure out how time is dilated, the time that you would measure, equals this Lorentz factor times what the real time that passage for that person in the other reference frame. See, reference frames are important here. Now that's just for the curious. I don't have you do these kind of calculations, but it brings us to the twins paradox. Not really a paradox. It's just, if you think about this classically, which we're all trained to do, it feels like there's a paradox, because if I observe a train going past me and you're on that train and you're moving really, really fast, I would say your clock is going slower. But you on the train would look like I'm the one that's moving relative to you. So you go, nope, you're wrong. Your clock is going slower. There has to be a resolution to that. And the idea here is, let's do another thought experiment called the twins paradox. Consider we have two 20-year-old identical twins. Both these people are astronauts, but one doesn't hops onto a spaceship and that can travel at an average speed of 0.999 c, 99.9% of the speed of light. So these two twin sisters, the woman that gets on the spaceship just, takes it out for a joyride, travels to a planet 30 light years away, does a quick little dance, and turns around and comes back to the Earth. So for the person watching, for the twin watching the sister fly away on a spaceship, they would say, oh, her clocks are running slower. She's moving at 99.9% of the speed of light. However, for the person on the spaceship, they would say, no, the person on the Earth is receding away from me and then I'm barreling back towards it. Their clocks are running slower because they're moving relative to me. The question is, does it all come out in the wash? And whenever the twin sister returns back to the Earth, are they the same age? Or if it looks like the person that went out and came back, their clocks were running slower, then the person that went out and back should be younger than the twin that remained on Earth. Or would it be the case that the person went out and back, it looked like the Earth was going away and coming back, that person should be younger? There's a lot to consider right here. Let's see how it plays out. Okay, so let's actually do, the thing that's important is you have to consider the person that's doing the actual accelerating, which is going to be the twin on the spaceship. So our twin on Earth waits 60 years, a little bit longer, but close to 60 years, because it's moving almost at the speed of light and you're going 30 light years away. So they have to wait 60 years for their sister to go all the way out and come 30 light years away and come all the way back. They were 20 whenever this experiment started. Then they waited 60 years for their twin to come back. So how old are they? They would be 20 plus the 60 years. They would be 80 years old. The twin on the spaceship, though, time is running differently for them. And time is running slower. We could actually calculate it out. We could use our Lorentz factor. We could plug in the 0.999c. See that time has been dilated by a factor of 22.36. So what does that actually end up meaning? That person doesn't experience 60 years of time. They experience only 2.68, about 3 years of time. Let's just round it to 3 for ease of discussion. So the twin that went out for 30 light years and then came back to the Earth, for them, only 3 years passed. So when they get back to the Earth, they're 23 years old, while their twin sister is 80 years old. This sounds ridiculous, right? But it's true. This is how it would work. This really would happen. And you can't just flip the situation and make the argument that, oh, well, why don't we just time dilate the person on the Earth? Because there's a trick. There's a difference that you could be measured and be felt and be experienced for the twin. For the person that's just on Earth, they're just on Earth. They're just sitting there. For the person on the spaceship, they're accelerating and then turning around. So accelerating to make the turnaround and accelerating again. And in that, the acceleration, the time trick happens, which makes the twin paradox actually come out. To really understand this, you need to go through some Lorentz transformations and things like that. If you want an alternate explanation that's pretty quick and actually has some graphics that go along with it, still mind-boggling and kind of hard to follow, there are some minute physics videos that I have put in the week 14 README. So I hope you'll go and watch those. And I hope you now have an appreciation that special relativity is weird. The things to walk away from here, things that are moving at reference frames that are moving at high speeds, clocks run slower, and there is no special reference frame. All right, I will see you when we talk about general relativity, where things get stranger still.